You think you understand a second, a tick of a clock, a blink, a heartbeat, but strip away the illusion and you find something else. 9,192,631,770. Vibrations of a Cesium-133 atom. That is the second, not the rotation of Earth, not the orbit around the Sun. A shivering atom locked at absolute zero. And inside that single second lies an infinity you cannot touch. Louis Essen built the first Cesium clock at the National Physical Laboratory in the United Kingdom in 1955. By 1958, a collaboration between Essen and William Markowitz measured the Cesium frequency over 2.75 years. They arrived at 9,192,631,770 Hz, with an uncertainty of plus or minus 20 Hz. The definition accepted internationally uses that exact number. Before this, we defined the second as 1 divided by 86,400 of a mean solar day. The Earth is a terrible clock. Its rotation fluctuates. Irregularities pile up. Cesium does not waver. They pass through intense microwave energies, sweeping backward and forward across frequencies. At exactly 9,192,631,770 cycles per second, the atom changes its energy state. Another magnetic field at the far end separates the atoms that changed. A detector counts them. Peak output means perfect frequency. That frequency divided by 9,192,631,770 gives 1 pulse per second. The best Cesium fountain clocks today reach uncertainty below 2 parts in 10 to the 15th power. They lose 1 second every 1.4 million years. But even that pales against what unfolds in the spaces between matter itself. Take an atom. Any atom. The nucleus occupies the center. If that nucleus were the size of a peanut, the atom would span a baseball stadium. The electrons exist somewhere in that vast expanse. Classical thinking says the rest is empty. Classical thinking is wrong. Quantum field theory describes all of space as filled with fields. Electromagnetic fields, electron fields, quark fields, gluon fields. Even at absolute zero, with no particles present, these fields fluctuate. Werner Heisenberg proved in his uncertainty principle that energy and time obey a relationship. The change in energy multiplied by the change in time must be greater than or equal to 1/2 of the reduced Planck constant. That constant equals approximately 5.27 times 10 to the negative 35 joule seconds. This means temporary violations of energy conservation can occur over infinitesimally brief intervals. Particle-antiparticle pairs pop into existence. They exist for a duration so short that the universe does not register the violation. Then they vanish. These are virtual particles. They are not directly observable, but their effects are measurable. The external pressure pushes the plates together. Scientists confirmed this experimentally in 1958. The Casimir effect proves the quantum vacuum is real. Empty space seethes with energy. Cosmological observations suggest 10 to the negative 9 joules per cubic meter. This discrepancy spans 122 orders of magnitude. Physicists call it the vacuum catastrophe. Something fundamental about the vacuum remains unknown, but experiments confirm virtual particles influence real matter. The Lamb shift in hydrogen atoms, measured in the 1940s, showed energy level splitting caused by interactions with vacuum fluctuations. Electron magnetic moments differ from predictions when you ignore the virtual particle C. Stephen Hawking proposed in the 1970s that virtual particle pairs near black hole event horizons cause Hawking radiation. One particle falls into the black hole, the other escapes. The black hole loses mass. Over eons it evaporates. Calculate it from the reduced Planck constant, the gravitational constant, and the speed of light. The result is approximately 5.39 times 10 to the negative 43 seconds. This is the time it takes light traveling at light speed to cross 1 Planck length, which equals 1.6 times 10 to the negative 35 meters. Below the Planck time, the concept of time itself breaks down. Anything that happens faster cannot be measured. In that unmeasurable zone, particles borrow energy from the vacuum and pop into existence as long as they vanish before the Planck time expires. 1 Planck time compared to 1 second is like 1 second compared to 10 million times the age of the universe. In 1 second, approximately 1.85 times 10 to the 43rd Planck times pass. Each one a window where quantum chaos erupts unseen. But during that second, at scales below our measurement threshold, the fabric of reality churns. Space is not a stage. It is an actor. The cloud represents all the places the electron might be found if you measure it. The densest regions are where you are most likely to detect it. The orbital is defined as the region where there is a 90% probability of finding the electron. Outside that region, the probability does not drop to zero. It tapers off. The electron wave function extends throughout all space. Near the nucleus, the probability is high. Far away, it becomes negligible but never zero. This is not emptiness. This is a continuous quantum field. Add the electron field, the quark field, the gluon field, and others. There is no classical void. Even the nucleus is not a collection of hard spheres. Protons and neutrons are made of quarks. 3 quarks per nucleon. But inside each proton or neutron, a boiling soup of virtual quarks constantly appears and disappears. Gluons hold the quarks inside a radius of 0.9 femtometers. 1 femtometer equals 10 to the negative 15 meters. The interior of a proton is the most complex place in the universe. Saying atoms are 99.99% empty space is like saying a hurricane is mostly empty space because air molecules are far apart. The space is filled with energy motion and interaction. Also, comment from which city you are hearing this from. Also, this script is researched and factual using sources from the Wikipedia article on Cesium standard, published 3 weeks ago in December 2024, confirming the exact definition of the second and the 1967 decision and the physical review letters measurement from Essen and Markowitz. The quantum fluctuation details come from the Wikipedia article on quantum fluctuation published November 26, 2025, and the vacuum energy article from Wikipedia updated 3 weeks ago in late December 2024. The Planck time calculations are from the Wikipedia article on Planck units updated 2 weeks ago in late December 2024, and the article from Ocean Mountain on minimum length and time, which provides the theoretical framework. The attosecond measurements of electron dynamics come from the Nature Communications paper on xenon photoionization from October 2020 and the PENUS paper from June 2017 on electron scattering and transition metals. These are peer-reviewed experimental papers, not popular science speculation. Now back to the information. Those atoms are made of electrons, protons, neutrons. Those particles are made of quarks and leptons. Those are made of vibrating quantum fields. At every level, what appears solid is actually probability waves interacting. When you touch a table, your hand does not actually contact the table. The electron clouds of your hand atoms and the table atoms repel each other through electromagnetic force. The repulsion happens because electrons are fermions. The Pauli exclusion principle forbids 2 fermions from occupying the same quantum state. The force you feel is electrons refusing to overlap. Empty space has nothing to do with it. The void between nucleus and electron is filled with the electron's own wave function, and with fluctuating quantum fields. Attosecond science studies electron motion. 1 attosecond equals 10 to the negative 18 seconds. 1 second contains 1 quintillion attoseconds. In 2023, the Nobel Prize in Physics went to Pierre Agostini, Annie Louillet, and Ferenc Krauss for methods that generate attosecond pulses of light to study electron dynamics in matter. Experiments measure photoionization time delays. When a photon strikes an atom and ejects an electron, the process takes time. In xenon, atoms' photoionization of the 4d inner shell electron shows time delays of 100 attoseconds between different spin-orbit states at threshold energies around 75 electron volts. These measurements, published in Nature Communications in October 2020, used attosecond interferometry and coincidence spectroscopy. Another experiment from 2017, published in PNAS, measured electron scattering in copper and nickel. Photoelectrons from nickel's D band have lifetimes 100 attoseconds shorter than those from copper's D band. This difference comes from enhanced electron-electron scattering in nickel's unfilled D band. Electronic rearrangement after photon absorption. All of this happens in less than a femtosecond. A femtosecond is 1 quadrillionth of a second. Inside that femtosecond attosecond, dynamics play out. Inside an attosecond, nothing we can measure occurs, because we reach the resolution limit of current technology. But the Planck time sits 25 orders of magnitude below the attosecond. Between measurement and the Planck floor lies an abyss of activity we cannot access. Experiments at Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada showed that neutrinos change type as they propagate. Solar neutrinos produced in the sun arrive at Earth with different flavor ratios than predicted. Atmospheric neutrinos created when cosmic rays hit the atmosphere also show flavor changes. The Ice Cube detector at the South Pole recently published results in May 2024 using 150,000 candidate neutrino events collected over 10 years. They measured oscillation parameters with unprecedented precision. The T2K experiment in Japan sends neutrinos 295 kilometers from the J-Park accelerator to the Super Kamiokande detector. In January 2024, T2K entered a new phase with enhanced beam intensity of 710 kilowatts and new near detectors. The NOVA experiment in the United States sends neutrinos from Fermilab 810 kilometers to a detector in Minnesota. In October 2025, T2K and NOVA published the first joint analysis in Nature combining their datasets. They placed new constraints on neutrino mass ordering and CP violation. Around 2.5 times 10 to the negative 3 electron volts squared. For comparison, the electron mass is 511,000 electron volts. Neutrinos are ghosts. Trillions pass through your body every second from the sun. They do not interact. They slip through matter as if it were empty space. But even they obey the quantum rules. Their wave functions spread. They exist in superposition. They are probability clouds traveling at near light speed. Reality at the smallest scales is nothing like the macroscopic world of clocks and calendars and human perception. The T2K experiment is undergoing further upgrades to reach 1.3 megawatts of beam power. With upgraded electromagnetic horns, the collaboration expects to observe 3 times as many neutrino interactions per unit time. The NOVA experiment completed a major data collection phase with 13.6 times 10 to the 20th protons on target. The combined analysis with T2K represents the most comprehensive neutrino oscillation measurement to date. Attosecond science advances. The European XFVL in Hamburg uses the world's largest X-ray laser to study quantum vacuum fluctuations. In 2015, researchers at the University of Konstanz claimed to directly detect vacuum fluctuations by observing their influence on light waves. In 2017, they reported manipulating the vacuum itself by squeezing it and detecting changes in quantum fluctuations. These experiments remain debated, but they push measurement into previously unreachable domains. A 2016 paper in the European physical journal C by Mir Faisal Mohammed Khalil and Surya Das suggested the minimum measurable time could be much larger than 10 to the negative 43 seconds. This would alter the basic equations of quantum mechanics. Time might have a crystal structure made of discrete, regularly repeating segments. Tests using the spontaneous emission rate of hydrogen atoms could measure this. The proposed effects might also appear in decay rates of particles and unstable nuclei. If time itself is granular, then the space between the grains is where meaning dissolves. A cesium atom oscillates 9 billion times. An attosecond laser pulse can trigger 10 quintillion electron movements. Virtual particles appear and vanish 10 to the 43rd times per Planck interval across every cubic meter of space. The vacuum energy density calculated from quantum field theory is 10 to the 113th joules per cubic meter if the theory is taken literally. Observations show 10 to the negative 9 joules per cubic meter. The discrepancy is called the cosmological constant problem. Either the theory is wrong, or something cancels almost all the vacuum energy. Dark energy makes up 70% of the universe's energy content. Its nature is unknown. It might be related to vacuum energy. If so, then the quantum fluctuations in empty space drive the accelerated expansion of the cosmos. The fate of the universe rests on the activity in the void. Quantum mechanics is not incomplete. It is complete and strange. The electron does not have a definite position until you force it to have one by observing it. Observation is a physical interaction. The interaction changes the system. Heisenberg's uncertainty principle is not about measurement error. It is about the fundamental nature of reality. You cannot know both position and momentum precisely because those properties do not exist precisely until measured. A virtual particle with the mass of a W boson which mediates the weak nuclear force can exist for around 10 to the negative 26 seconds. These durations are far longer than the Planck time. The Planck time is the absolute floor. Below it, the notions of distance and time become meaningless. Space-time itself may be quantized. The smooth continuum we experience at macroscopic scales might be an illusion. At the Planck scale, space-time could be a foam of fluctuating geometry. John Wheeler proposed this in 1955. He called it quantum foam. Evidence for it remains elusive because we cannot probe lengths smaller than 10 to the negative 18 meters with current technology. The Planck length is 10 to the negative 35 meters. We are 17 orders of magnitude away from testing the idea directly. What does this mean for the second? The second is a human construct, a convenient division of time based on the regular oscillation of a specific atom. But time itself is not human. Time is a dimension of space-time. It can dilate, move fast, or enter strong gravity and your clock slows relative to another observer. This is not perception. It is measured fact. Atomic clocks on satellites tick faster than atomic clocks on Earth's surface. The difference is small, around 45 microseconds per day for GPS satellites, but the effect is real. Gravitational time dilation follows from general relativity. Experiments confirm it. In 2024, researchers published results showing atomic clocks, separated by 1 centimeter in altitude, detect time dilation due to Earth's gravity. The precision of strontium lattice clocks reaches 10 to the negative 18 seconds. They measure time at the attosecond scale by tracking the oscillations of strontium atoms trapped in an optical lattice. These clocks are so precise, they reveal time dilation effects at the scale of centimeters. Peel away the foam, and you find equations. Peel away the equations, and you find mathematics. Peel away mathematics, and you find the unknowable. The number of such events in 1 second across the observable universe is beyond comprehension. If the observable universe contains 10 to the 80 atoms, and each atom occupies roughly 10 to the negative 30 cubic meters, then the universe contains around 10 to the 110 cubic meters of space. In 1 second, in 1 cubic meter, 10 to the 43 Planck intervals occur. Across 10 to the 110 cubic meters, that is 10 to the 153 Planck intervals. If even one virtual particle pair appears per Planck interval per cubic meter, the total number of virtual events per second in the observable universe is 10 to the 153. That number has no name. It is larger than a Google raised to the Google power, and this is a conservative estimate. Quantum field theory suggests far more activity. The standard model of particle physics describes 3 of the 4 fundamental forces using quantum field theory. It is the most successful theory in physics. It predicts the electron's magnetic moment to 10 decimal places. It predicted the Higgs boson, which was discovered at the Large Hadron Collider in 2012. It works because it accounts for virtual particles and quantum fluctuations. The electrons in your atoms are excitations of the electron field. The quarks in your protons and neutrons are excitations of the quark field. The photons of light that let you see are excitations of the electromagnetic field. At the most fundamental level, there are no particles. There are only fields. Particles are what we call localized excitations of fields. When a field vibrates in one place, we detect a particle. When the vibration spreads out, we see a wave. Wave-particle duality is not a paradox. It is a feature of quantum field theory. The field is fundamental. The particle and wave are emergent descriptions. In quantum mechanics, time is a parameter in the Schrödinger equation. The wave function evolves in time, but time is not an observable in quantum mechanics. You cannot measure time the way you measure position or momentum. Time is the backdrop against which measurements occur, except at the Planck scale, where the backdrop itself becomes uncertain. Time might arise from more fundamental quantum entanglement. The entanglement structure of quantum states could give rise to the experience of temporal flow. This is speculative. No experiment tests it yet, but the idea challenges the notion of time as fundamental. If time emerges from something deeper, then asking what happens in 1 second is like asking what happens in 1 degree of temperature. The question presumes time is a thing. It might not be. Hawking radiation remains unobserved directly, but the theoretical framework is solid. Experiments on analog systems in labs show Hawking like radiation in sonic black holes and optical analogs. The International Atomic Timescale averages over 400 Cesium clocks in laboratories around the world. Coordinated universal time adds leap seconds to stay aligned with Earth's rotation. But the atomic time marches on independent of the planet. This is time freed from the heavens, time locked to the quantum world. Total mass, number 133, 1 valence electron in the 6s orbital. The nucleus has spin 7 halves. The electron has spin 1 half. Hyperfine splitting occurs when the nuclear spin and electron spin couple. 2 energy levels result. The transition between them produces radiation at 9,192,631,770 Hz. That frequency is in the microwave range. The wavelength is about 3.26 centimeters. This is the standard. Every cesium clock exploits this transition. Tune the microwave field to match the natural frequency of the atom, and the atom responds. Count the cycles. Divide by the magic number. You have 1 second. We chose cesium because it is stable, reliable, and reproducible. Any lab anywhere can build a cesium clock and get the same result. The second is now defined by a physical constant, not by the motion of celestial bodies. This is the triumph of modern metrology. Time is no longer tied to human scale phenomena. It is tied to atomic scale quantum transitions. The electron wave function extends to infinite distance. The probability tapers off, but never reaches 0. The electric field of a single proton extends to infinite distance following an inverse square law. The quantum vacuum supports fluctuations at all frequencies up to the Planck scale. The sum of all vacuum energies over all frequencies is formally infinite. Renormalization procedures in quantum field theory subtract infinities to get finite observable predictions. This works mathematically, but the physical meaning of the infinities remains debated. Perhaps loops of space-time. Perhaps something else. The second spans all these layers. It is defined at the atomic scale. It is experienced at the human scale. It contains activity at the Planck scale. All of this is true simultaneously. This is physics, confirmed by experiment after experiment. The quantum world is the real world. The classical world is an approximation that works at large scales and slow speeds. When you look closely, when you measure precisely, the approximation breaks down. The weirdness emerges. Electrons in your eyes absorb photons and trigger chemical reactions that send signals to your brain. Those reactions occur in nanoseconds. Neurotransmitters cross synapses in milliseconds. Your subjective experience of the second is constructed from countless quantum events. You do not perceive the quantum scale, but it underlies everything you do perceive. Harold Lyons at the National Bureau of Standards made one of the first assessments of cesium frequency in 1952, but his beam standard could only operate for short periods. Louis Essen received funding at the National Physical Laboratory in 1953 and within 2 years had a reliable version running. The collaboration between Essen and Markowitz compared atomic time to astronomical time over 2.75 years. They used shortwave time signals broadcast by WDWE. The National Bureau of Standards operated this station, transmitting at frequencies that bounce off the ionosphere and can be received across continents. Essen in England and Markowitz in the United States simultaneously received WDWV signals to synchronize their measurements. By today's standards, the technique was crude, but it worked well enough to define the second. The measurement published in Physical Review Letters, Volume 1 in 1958, gave the cesium frequency as 9,192,631,770 plus or minus 20 Hertz. The uncertainty of 20 Hertz divided by 9 billion gives relative uncertainty of about 2 parts in 10 to the 12th power. Extraordinary for the 1950s. Modern cesium fountain clocks achieve relative uncertainties below 2 parts in 10 to the 15th power, 1,000 times better, but the defined value has not changed. Improving clock precision does not change the definition, it only allows us to realize it more accurately. The photon energy matches the hyperfine splitting energy. The atom absorbs the photon. The electron's spin flips relative to the nuclear spin. This is a magnetic dipole transition taking real time with a natural line width related to the lifetime of the excited state. For the cesium ground state hyperfine transition, the natural line width is extremely narrow, giving the transition its stability. It interacts with surrounding fields. Electromagnetic vacuum field, stray magnetic fields. These interactions cause shifts. The Zeeman effect splits hyperfine levels in magnetic fields. Blackbody radiation causes shifts. Modern cesium fountain clocks operate in ultra-high vacuum with magnetic shielding. Atoms are cooled to microkelvin temperatures using laser cooling. At such low temperatures, atomic velocities reduce, narrowing the Doppler broadening. The atoms are launched upward in a fountain, rising under gravity, then falling back down. During their ballistic trajectory, they interact with microwave fields twice. This Ramsey interrogation technique increases interaction time and improves precision. Operation in 1999 with uncertainty about 3 parts in 10 to the 16th power. International Atomic Time, TAI, averages data from over 400 atomic clocks in more than 70 laboratories worldwide. Optical clocks based on strontium or ytterbium are even more stable, operating at 430 terahertz. That is 4.3 times 10 to the 14th oscillations per second, compared to 9 billion for cesium. Higher frequency means better resolution. By 2030, the second may be redefined based on optical transitions. The Large Hadron Collider reaches 14 tera electron volts. The Planck energy is 1 billion times higher. We are nowhere close to probing Planck scale physics directly. Loop quantum gravity quantizes space-time into discrete units. All approaches agree something new happens at the Planck scale, but we have no experimental evidence yet. The path integral formulation sums over all possible paths. In quantum gravity, this means summing over all possible space-time geometries, including wildly fluctuating ones at small scales. These fluctuations contribute to vacuum energy and make space-time uncertain below the Planck scale. You cannot specify a location more precisely than 1 Planck length, or time more precisely than 1 Planck time. This is not measurement limitation. It is space-time itself. If true, there are infinitely many copies of you in infinitely many parallel universes. Each copy experiences different measurement outcomes. The second is the same in all branches, but measurement outcomes differ. The wave function splits. Both outcomes occur, but you only experience one branch. You perceive snapshots stitched together into a narrative of continuous flow. Neural signals propagate in milliseconds. Conscious perception integrates over hundreds of milliseconds. By the time you perceive the second, it is long past. You live in your brain's reconstruction of recent past. The clock measures in real time. It does not think, it measures objectively. Move at high speed and your clock slows relative to a stationary observer. GPS satellites orbit at high speed and weak gravity. Both effects influence their clocks. Special relativity makes them tick faster. General relativity makes them tick slower. Net effect is about 38 microseconds per day faster. Without corrections, GPS would drift 10 kilometers per day. Space-time is fundamental. Space and time separately are observer-dependent. Now return to the void, the quantum vacuum filled with energy. This energy contributes to the cosmological constant and affects the Higgs field. It renormalizes particle masses and charges. Without vacuum energy, electrons would have infinite mass. Infinities plague quantum field theory appearing in particle interaction calculations. Renormalization removes infinities by redefining parameters. Bare mass and charge of particles are infinite. Observed mass and charge are finite because they include screening effects from virtual particles. Dark energy makes up 70% of the universe. Dark matter is 25%. Ordinary matter is 5%. We understand about 5%. Everything we see and measure is a tiny fraction. The universe is mostly dark. Dark energy pushes space apart, accelerating expansion. Discovered in 1998 by observations of distant supernovae. If dark energy is vacuum energy, then quantum fluctuations drive cosmic expansion. The activity in the void tears space apart. The second provides the ruler. The second was measured by comparing cesium oscillations to Earth's rotation over 2.75 years by Louis Essen at the National Physical Laboratory in the United Kingdom and William Markowitz at the United States Naval Observatory. The measurement was published in Physical Review Letters in 1958. The final value, 9,192,631,770 Hertz, had uncertainty of plus or minus 20 Hertz. This was the basis for the 1967 definition adopted by the International Committee of Weights and Measures. The comparison was done using shortwave time signals broadcast by NBS radio station WWWV, then located on the East Coast. This setup allowed timing comparison across the Atlantic. The entire foundation of modern time rests on a 2.75-year measurement done in the 1950s using radio signals between continents. The precision has been surpassed, but the defined value remains. The second is locked to those 1958 transmissions. Every cesium clock since reproduces that standard. They are launched upward. Microwave cavities interrogate them. Detectors count atoms that made the transition. Computers analyze data. Error corrections applied. The clock outputs 1 pulse per second. This signal distributes via GPS satellites to users worldwide. Banks use it for timestamping. Power grids use it for synchronizing phases. GPS receivers use it for position. Scientific experiments use precise timing. The second keeps civilization running. Each nucleon contains quarks. Each quark is an excitation of the quark field. Quantum fields fluctuate. Virtual particles appear and vanish. The Lamb shift, the electron magnetic moment. The void keeps its secrets, yet those secrets underlie all of reality. We tame them with mathematics. We extract finite predictions matching experiments, but the infinities remain as features, not errors. The resolution lies in quantum mechanics. The finite observable collapses from the infinite superposition. Measurement selects one outcome from infinite possibilities. The wave function spans all states. The measurement yields one state. You observe the finite. The infinite remains hidden. The void is infinite. The second is how we measure it.